Well, thank you very much for these kind words. There are a lot of these events that I've forgotten, and thank you for reminding me. And it's a real honor to be here. This is my third time in Korea, and I'm enjoying it very much. And thank you, Professor Ko, for organizing all this. Okay, so I'll talk about large-scale geometry, and in particular, large-scale geometry of mapping class groups. But I'll start by reminding you what large-scale geometry is. So the idea of studying groups as metric spaces is due to Gromov, and he has developed a rich field of mathematics thinking in those terms. So the story starts by thinking about a group G that's generated by a finite set, so a finitely generated group. So S is going to be a finite generating set. And for convenience, we'll think about the set being closed under taking inverses. And then to this one associates a topological object, or a geometric object if you want, namely the Cayley graph of the group. Okay, so let's call it X. This is really X of GS, and this is the Cayley graph. Cayley graph. And how is it defined? Well, the vertices are the elements of the group. So the vertices are elements of G. So you just imagine a discrete set in bijection with the group G. And then the edges, you draw an edge if two elements differ by an element of S. So in other words, you have an element of the group G, and then you join it to GS whenever S is in S. Okay, so whenever you see two elements G and GS like this, you put an edge between them. Okay, so for example, let's say our group is Z plus Z. So just a free abelian group of rank 2, and I'm going to take the simplest possible generating set. So I'll take S to be plus minus 1, 0, and 0 plus minus 1, like this. Then what's the graph I get? Well, you get the usual grid in the plane. You get this kind of a graph. The vertices are just integer points, and then the edges will have length 1 in the Euclidean plane, and they will join 2 points either horizontally or vertically, depending on whether this element S is 1, 0 or 0, 1. Okay, so that's the Cayley graph in this case. Okay, for another example, let's suppose we take a free group. So let's say a free group of rank 2 generated by two elements A and B, say. And then our set S is going to consist of A inverse, B, and B inverse. And then the graph you obtain is going to be a 3. So it's like this. Okay, so these horizontal edges, maybe this point corresponds to the identity element, and then this point over here is maybe A, this is A inverse, this is B inverse, this would be AB, and this would be BA over here. So in this group here, A and B commute, so these 2 points would coincide, and you will get a little square. Well, in the free group, they don't coincide, so you get a 3 like this. Okay. And now this graph comes with a metric, namely the path metric. I can declare that every edge has length 1, and then I can measure the distance between two vertices in the graph by just looking at the shortest possible path that connects them, and then counting how many edges I cross. Okay, so there is a notion of a path metric. So this X is equipped with the path metric. Okay, so the distance between any two vertices, what's really relevant is just the metric on the vertices, or you can easily extend it to any 2 points in the graph, but we'll just think about measuring the distance between the vertices. So the distance between, let's say, G and H, two elements, two vertices represented by the group elements G and H, this is going to be the length of the shortest edge path from H to G, from G to H. And this is really the same thing as the norm of G inverse H. This is the norm with respect to this generating set S. Namely, take this group element, G inverse H, and represent it in a minimal way as a product of generators. So this is the minimal n, so that this G inverse H is a product of n generators, so that the SIs are all in S. Okay. So, for example, if you take the identity element and you take the element 1, 1, then the word norm of this element is 2, because you can write it as either as the horizontal generator times the vertical, or vertical times horizontal, but the minimal length is 2. So you just measure the distance between any two vertices, and that's your metric. Okay? Okay, so now how does one talk about large-scale invariance? So what are large-scale invariants? Okay, so there is some ambiguity here. I'd like to define a space where I don't necessarily choose a generating set. Maybe the group is finitely generated, but I don't really want to make a particular choice of the generating set. Or alternatively, I can think about making these Cayley graphs with respect to all possible generating sets, and then think about what they have in common. So if you change the generating set, then how does the metric change? Well, it changes in a Lipschitz way. I get a new metric, but the two metrics are comparable. They differ. Each is bounded by a constant times the other metric. Okay, so I'd like some concept where changing a metric like this is allowed, where I don't really have a metric space with a fixed metric, but the metric is allowed to be changed in this way. Okay, where you replace it with another metric that's Lipschitz equivalent. So there is a notion of a quasi-isometry. So there is a certain equivalence relation among metric spaces. Equivalence relation among metric spaces. And there are really two operations. So this relation is called quasi-isometry. So there are two operations. So this is generated by two operations. Okay, so the first operation is you're allowed to change the metric, but the new metric has to be Lipschitz equivalent to the old one. Okay, so x d1 is equivalent to x d2 so it's the same underlying set, x, but just two different metrics. If there is a constant k greater than 1, say, greater than or equal to 1, so that d2 is less than or equal than k times d1, and it's greater than 1 over k times d1. Okay, so no matter what pair of points you put in, the distance 2 is bounded below and above and below by some constant times the other metric. Okay, so the main example here is changing the metric. So if S prime is another generating set, another finite generating set, okay, then the group G with the metric explained over here with respect to S. So maybe I'll just call it D sub S. Okay, so this is what I mean by D sub S. It's the metric that comes from this finite generating set. Then this is equivalent to G with respect to ds prime. Namely, you would just look at the elements of S. You express them as products of elements in S prime, and you look at the longest such product. If let's say it's 10, and you do it the other way around. You express every element of S prime as a word in the elements in S. And there's some bound, because all these sets are finite. And that bound K will then, they'll get these inequalities that satisfy. This inequality will hold with that K. Okay? So changing the generating set does not affect this equivalence relation. Yes?
Do I see this correctly, that this is the first time you need that the group is finitely generated?
That's right. I mean, I could define the Cayley graph with respect to an infinite generating set, and sometimes that's done. But then I would not have this property here. Yes. Okay. Now the other operation is passing to co-bounded subsets. So if I take, so I'm just going to declare that x with any metric d is equivalent to y with the same metric d, or the restricted metric. So if y in x is co-bounded. And what I mean by co-bounded is that there exists some number r, say, so that any metric ball of radius r in x intersects y. So there exists some fixed r, so that for every x in x, the ball centered at x with radius r intersect y is non-empty. Okay, so in other words, this subset y is dense in this sense here. It's R dense. There are no big holes in the complement. You cannot draw a very large ball in the complement. So an example of this is, for instance, z inside R. Right. So z is co-bounded in R. If I take any ball of radius more than half, let's say 1, in R, then that's an interval of size 2 that will have to contain an integer point. And so I'm just going to declare that those spaces are equivalent in this equivalence relation. Okay, another example of this is if I take a finitely generated group and I take a subgroup, which is a finite index. Okay, then this G is equivalent to H by this, and by the metric I mean the metric, the word metric that comes from that construction here. So when I pass to, so first of all, it doesn't, if G is finitely generated, it doesn't matter what generating set I put on. All those metrics will be equivalent. And then passing to a finite index subgroup, the point is those subgroups are all co-bounded in this sense here. So replacing a group by a finite index subgroup does not change the equivalence class. There's actually a famous theorem that generalizes this observation here, that the Z and R are quasi-asymmetric. And this is sometimes called the fundamental theorem of geometric group theory. And it's attributed to Schwarz and Milner and Schwarz. This is not joint work, it's just independent observations. This is not a very hard theorem, it's important because it's used all the time. And it just says that if you have a group G, so G is acting on some space X. So X is a metric space. And G is a finitely generated group. And the action is properly discontinuous. Discontinuous, isometric, and co-compact. Okay. Then this implies that in fact G and X are quasi-isometric. They're equivalent. So G with the word metric and X with the given metric. And I should say X has a path metric space. Path metric space. So its metric is obtained by minimizing the length of a path between 2 points. Okay, so this is an example. Z is acting on R by translations, and all those conditions hold. So Z and R are quasi-isometric. But there are many other examples. Well, we already drew the picture for the free group, but the free group is acting by deck transformations. If you think of this as the universal cover of a graph, then the free group is acting on the tree, and all those conditions hold. So the free group is quasi-asymmetric to the tree. But you can generalize this to, for instance, the fundamental group of a surface of genus at least 2. This is quasi-isometric to the hyperbolic plane. Why? Because the universal cover of the surface can be identified with the hyperbolic plane. You can put a hyperbolic structure on the surface so that the metric, it's a Riemannian metric which is locally isometric to the hyperbolic plane. So the universal cover is isometric to the hyperbolic plane, so the fundamental group is acting on the hyperbolic plane, and these conditions hold. And so this group, fundamental group of a surface, is quasi-isometric to the hyperbolic plane. More generally, you can have a co-compact lattice acting on some symmetric space. Co-compact lattices are quasi-isometric to their respective symmetric space. Okay, this is a particular example of that. Okay. Are there any questions so far? Is this clear? So now we're ready to define what we mean by large scale. What is a large scale property? Okay, so a property of metric spaces is large scale if whenever x and y are quasi-isometric, so this is my symbol for x and y being in the same equivalence class, they're quasi-isometric, and x property P, say, and x satisfies P, and then y satisfies P. Okay, that's what large scale means. Okay, example. Well, we'll start with the non-example. Being connected. So being connected is not a large-scale property. For example, the Z is not connected and R is. Okay, so this is not large-scale. However, the idea of connectivity can be made into a large-scale property. So usually this is the philosophy, that you take some usual property of topological spaces and then you make it a large-scale invariant. And in this case, you can promote this being connected to coarsely connected. So being coarsely connected, and that is a large-scale invariant. And how does that work? Well, I just have to know that there exists some R, so that for any 2 points in the space, say x, so x is my space, there exists a discrete path. There's a sequence. So x equals x0, and then x1, x2. You think of that as being a discrete path between x and y. So I have x and I have y, and I want to find some kind of a sequence of points. I cannot use paths, right, to define connectivity because a discrete set could be quasi-isometric to something that should be connected. But I can use these discrete paths, and the requirement is that the distance between 2 consecutive points is less than or equal to r. Okay, so I'm allowed to make these hops of size r, and if I can connect any 2 points like that, then I call the space coarsely connected. And this is a large-scale property. If x is quasi-isometric to y, then y will also satisfy it, except the value of r could be different. It could be much larger. Right? I could, for instance, take z and I could multiply the metric by 1,000,000. Okay, so the z satisfies this property with r equals 1, but when I scale it by 1,000,000, then I have to replace r by 1,000,000. But it still holds for some suitable r. Okay, so that's the general philosophy, and I won't go through all the through too many examples of this sort. I will give you maybe a couple more, and then we'll get to the main topic of the lecture, which is asymptotic dimension. Asymptotic dimension is another large-scale invariant. And but before I'll give you two other examples. So another example is the growth rate. Okay, so here I will only define it for groups. So G is going to be a finitely generated group. And I'm going to look at the function f of r. R is now some number. And I'm just going to count the number of points in the group that have distance at most r from the identity. Right? So this is the number of G in G, so that the word norm of G with respect to a fixed generating set, which I did not even bother to name, but there's some underlying finitely generated set, so finite generating set, and I want to count how many words I have of length at most r. Okay, so that's a function. Now this function itself is not an invariant under quasi-isometry, because, for instance, if I just change the generating set, then the function will likely change. For example, if I add more generators, I'll probably have more group elements with length bounded by the same number. But the quality of the function, it turns out, is invariant. So I can talk about exponential growth. So I could say that G has exponential growth. And that just means that that means that there exists some alpha positive, so that f of r is greater than or equal than e to the alpha r, say. So again, if I change the generating set, then the function might change and the value of alpha might change, but the concept, the property of there existing an alpha so that this inequality holds will not change. So then you say that the function has, the group has exponential growth. For example, the free group here has exponential growth, and if you do a count, it'll be something like 4 times 3 to the r minus 1 or r, I don't know, exercise. It's either r or r minus 1. If r is 1, it's 4, so it's probably r minus 1. That's f of r. And G has polynomial growth. If there exists n and c, so that f of r is less than or equal than c times r to the n. So here it turns out that the n does not change if you change the generating set, but the value of the constant might. So for example, for z plus z, this n is 2. So you have quadratic growth. The number of points in a ball of radius r is roughly r squared times some constant. And there's a famous theorem of Gromov, which is really what kind of started this whole field, characterizing groups with polynomial growth. So G has polynomial growth. If and only if G is what we call virtually nilpotent. Virtually it refers to a finite mixed subgroup. And so nilpotent groups have polynomial growth, and therefore any group that contains a nilpotent subgroup as a subgroup of finite index is also of polynomial growth. And the amazing thing is the implication that polynomial growth implies virtually nilpotent. Okay. You can wonder about whether there's something in between, whether there are groups that don't have polynomial growth and don't have exponential growth. Those are called groups of intermediate growth, and there is so there are examples of groups of intermediate growth by Grigorchuk and others, but it's unknown whether there are finitely presented groups with intermediate growth. That's still a major open question. And it was first asked by Milner because this growth function is related to the growth of volume. If you take say a Riemannian manifold, closed Riemannian manifold whose fundamental group is this group G, So it'll suddenly be finitely presented because the manifold was closed. And you take the universal cover, and then you start measuring the volume of balls of radius r. So that function will behave just like the growth rate function for the finitely generated group. And Milner's question was whether you can ever get an intermediate function, the one that's neither exponential nor polynomial. And that's still open. Okay, and the final example is isoperimetric functions. Those are much studied now. And that's another one that I don't really want to, in the interest of time, I don't want to get into the details of, but I will just mention that. So this is example isoperimetric function. So if you have a space like a Euclidean space, let's say a Euclidean plane, so R2, this satisfies the quadratic isoperimetric function, isoperimetric inequality, isometric function. So if I take any curve in the plane, and I wonder about the area of the disk that this curve bounds, well, it'll be quadratic. So the area is going to be less than or equal than some constant times the length squared. So this function is quadratic. This constant doesn't really count. You just think about the quality of the function, just like in the growth case, and it's a quadratic function. Now, Gromov discovered that there are many groups where the function, the isoperimetric function, is linear. And that's a very nice class of groups that we think we kind of understand. So these are called the hyperbolic groups. And let's see, let's go over here. Okay, so somehow this notion of hyperbolicity was, I think, the real reason for the explosion in this subject when it occurred in the 80s. So a group or a space, a metric space, is X, say, is hyperbolic, or let's say delta hyperbolic, if every geodesic triangle is delta thin. Okay, so I take 3 points in the space and I draw geodesics joining them. So then this way I get a triangle. And now what I want to know is that this triangle is thin, in the sense that if I take the delta neighborhood of 2 of the sides, they have to completely cover the third side. Okay, so here's one delta neighborhood, and here is the other one, and they have to completely cover. So if this is A, B, C, so the geodesic from A to B should be contained in the delta neighborhood of AC. Oh, this just breaks. Union delta of BC. Okay, so if this is true for every geodesic triangle, then we say that the space X is delta hyperbolic. Or we say hyperbolic if it's delta hyperbolic for some delta. And the group is hyperbolic if it's Cayley graph is hyperbolic. Okay, so there's to actually justify this definition, you'd have to prove that hyperbolicity is invariant under quasi-isometries, and it is. Okay. And the reason I mention this is because of the theorem of Gromov again, that says that G is hyperbolic if and only if it satisfies a linear isoperimetric function. Okay, so Z plus Z is not hyperbolic. You only have a quadratic isoperimetric inequality. Free group is, geodesic triangle in a tree is completely thin. It degenerates to a tripod. So it's hyperbolic with delta equals 0. And then a hyperbolic plane is another model example of a hyperbolic space. Triangles in the hyperbolic plane look like this. And so it's going to be delta hyperbolic for a certain delta, like log 2 or something. Yes?
So in that theorem where graph group is hyperbolic, Cayley graph is hyperbolic. But when you
That's the definition.
But depending on the generators, you have different shortest paths in the graph.
That's right. So you have to prove. So to justify this, you have to really prove something. You have to prove that that being hyperbolic is invariant under quasi-isometries. Okay. So this is not right. So you're completely right. So to make this definition, you have to prove something. But it's true. That's not a particularly easy theorem. It's not. I mean, you have to. It's work. You have to prove that quasi-geodesics are Morse, if you know what that means. You have to get the geodesics go to paths that are not completely arbitrary, but they stay close to new geodesics. There's a uniform bound between the geodesic and the new space and the image of the geodesic in the old space. So okay. All right. Okay, so now we'll talk about asymptotic dimension. This is the part of the talk I enjoy most. I love talking about asymptotic dimension for some reason. You'll see why. It's a nice invariant. It was also introduced by Gromov. So asymptotic dimension. So to motivate this, let me remind you what the definition of a topological dimension is, or covering dimension. Okay, so recall. So if X is a topological space, or let's say a metric space, you can define it for topological spaces too. Metric space, then we say that the dimension, this is the usual covering dimension, is less than or equal to n, and what that means is that for every epsilon greater than 0, you can find a covering. There is an open covering, say u alpha of X, so that first of all the sets are epsilon small, so the diameter of u alpha is less than epsilon for every alpha, and so that every point of the space belongs to at most n plus 1 elements of u alpha. So every X in X belongs to less than or equal than n plus 1 elements of the cover, n plus 1 u alphas. Okay? So for example, the plane, Euclidean plane, has dimension 2, and maybe the thing to start with is showing that it's not more than 2. So why is the dimension less than or equal to 2? So example, dimension of 2. So why is that? Well, I can draw a clever covering. So in the picture, this won't look like open sets, but you can thicken them up to become open sets. Okay, so this is called the brick covering. Okay, so I take a covering like this, and you're supposed to imagine these bricks as being less than epsilon. They're very small bricks, and I take some small neighborhoods so that they become open sets, and every point is and at most 3 of them. Right? So this shows that the dimension is less than or equal to 2. Okay. Let's define now the asymptotic dimension. Okay, so X is now again a metric space. Okay, so what does it mean to say that asymptotic dimension of X is less than or equal to n? Okay, so what that means is that for every r, here this r will play the role of the epsilon, but here this r is large. Okay, think of r as being large. For every r, there exists a cover, and here it doesn't matter whether it's open or not. In this large scale stuff, You can always, replace sets by open sets if you feel like it, but it doesn't matter. There's a cover, say U alpha of X, so that so first of all, the diameter of U alpha is uniformly bounded, not necessarily by R, usually something much larger, but uniformly bounded. And second, something stronger than the multiplicity. It's not just that every point is allowed to belong to at most n plus 1 elements, but every R ball. If you take a metric R ball, it's allowed to intersect at most n plus 1 elements. So BXR intersects at most n plus 1 U alphas for every X. Okay, so now I claim that asymptotic dimension of the plane is at most 2. Okay, and it's the same picture. Except now the bricks are large. I draw them so large that that if you take an R ball, it'll look like this. So this R is very small compared to the size of the bricks. But they're all uniformly of the same size, or they're uniformly bounded, and they have this property number 2. That every ball intersects at most, every R ball intersects at most 3 of them. Okay? Okay, so what are some basic properties? Okay, so there's a product theorem, asymptotic dimension of X cross Y with, you get to pick some natural metric on the product, like L1 or L2, it doesn't matter. Okay, so this is the same theorem that holds for a topological dimension. So you can replace this by dimension, it'll still be true. If I take a subset, if Y is a subset of X, then asymptotic dimension of Y is less than or equal to asymptotic dimension of X. That's supposed to be obvious. Let me also so for the next theorem, which is most useful, I want to remind you of a classical theorem in topological dimension called the Hurewicz theorem. This is called the Hurewicz theorem, and it says that if I have, so for simplicity, let's say X and Y are compact metric spaces. Metric. And you have a map from X to Y, and you assume that the dimension of F inverse of Y is less than or equal to n for every Y. So the point inverses have dimension bounded by n. Then the dimension of X is less than or equal to the dimension of Y plus n. Okay? So that somehow generalizes the product theorem, because you could map the product to one of the factors, and this would imply it. Okay, well, there's a large-scale version due to Bell and Dernishnikov. And what it says is that if I have so I have a Lipschitz map from X to Y. This is Lipschitz. And X is a path metric space. Okay. And then I'm going to assume that for every R, the collection of point inverses of R balls. So F inverse, so I take F inverse of the ball by R, this collection. So that's the collection. Instead of taking single point inverses, you take inverses of all balls of radius R. So this collection should have asymptotic dimension less than or equal to n uniformly. Okay, so I don't want to belabor too much on this point, But the requirement is that each individual point inverse has asymptotic dimension less than or equal to n. And in addition, like in the definition here, you have to get a uniformly bounded cover so that something holds. Well, the bound should be uniform over all y's. So the most frequent application of this is when all these point inverses are actually isometric to each other. Okay, that's what happens in the group situation. And then you don't have to worry about this uniformity. Just then the condition is just that one of them has asymptotic dimension less than or equal to n. And then the conclusion is that asymptotic dimension of x is less than or equal to asymptotic dimension of y plus n. Okay? Okay, so what are some basic examples of this? So for instance, if I have a short exact sequence of groups, of finitely generated groups. So to talk about asymptotic dimension, I need to have finitely generated groups, because otherwise I won't have a well-defined metric space. So all these are finitely generated groups. Then this Belder-Nishnikov theorem is going to say that asymptotic dimension of B is less than or equal to asymptotic dimension of A plus asymptotic dimension of C. Because I can call this F, and I can use the theorem. Point inverses are A's, and inverses of balls are sort of thickened versions of A's. There's some sort of neighborhood of A, and those are all quasi-isometric to each other, so they all have same asymptotic dimension, which is this. So in particular, for instance, you can see that braid groups, for those of you who are familiar with braid groups, so the asymptotic dimension of a braid group is less than or equal than n minus 1. How do you see that? Well, it's so there's a short exact sequence, so a Berman exact sequence, I guess, like this, where you have to replace the braid group by the pure braid group, which has finite index inside, by pulling out one of the strands. You know, a pure braid with n strands becomes a pure braid with n minus 1 strands, and the kernel is fn minus 1. And so this fact here tells you that by induction that asymptotic dimension of Bn is less than or equal to n minus 1. There is so let's see, hyperbolic plane. Asymptotic dimension of the hyperbolic plane is less than or equal to 2. It's actually equal to 2. But the interesting thing for us is that it's less than or equal to 2. Why? Well, you need a map. There's a map from H2 to the real line that satisfies the Belder-Nishnikov criterion with point inverses one-dimensional. Now, what is this map? Now, the first thing that occurs might be that it's just a nearest point projection, but that won't work. Maybe I'll let you think about why it won't. But the one that does work is the projection whose point inverses are horocycles. So a typical horocycle is going to be mapped to its intersection with this line. Okay, so all these blue things are isometric to each other, so you don't have to worry about uniformity. They all have dimension 1. They're not quite isometric to the real line. They're real lines with some funny function, funny distance function on it, but they still have asymptotic dimension 1. You can also do this with symmetric spaces. So a symmetric space, if you have a group that has the KAN decomposition, then the symmetric space is G mod K, and that's AN. And so you can map this to A, and then the fiber is N. And for the same reason, so this is a nilpotent Lie group. You can prove that nilpotent Lie groups have asymptotic dimension bounded by their dimension. This is, I guess, for simply connected Lie groups. Also by using inductively the short exact sequence, short exact sequence for Lie groups, and then you use the Belder-Nishnikov theorem one more time for the projection to A. And you conclude that the symmetric space also has finite asymptotic dimension. And in fact, its asymptotic dimension is equal to its dimension, just like for H2. And so, for example, lattices and Lie groups all have finite asymptotic dimension. Okay. A tree has asymptotic dimension at most 1, and you can use this the same theorem to do this. So asymptotic dimension of a tree is less than or equal to 1. So you think about the tree as being something like this, and it's sort of hanging down, and you map it to the real line just by the sort of height function. You hang the tree by a point, and you map it to the real line, and you check the Bell-Dranishnikov criterion for this. You argue that point inverses or interval inverses, so the typical ball is this, interval inverses have asymptotic dimension 0. Okay. There's a theorem of Gromov that every hyperbolic group, so if G is hyperbolic, then it has a finite asymptotic dimension. And there was a sharpened version of this by Buyalo, that the asymptotic dimension of the group is actually equal to the dimension of its boundary. So every hyperbolic group has a space at infinity that's defined by looking at geodesic rays. You go to infinity, then plus 1. And somehow the proof of this is really modeled on the proof of trees. This asymptotic dimension of point inverses is really controlled by the sort of a Cantor set at infinity here, which is 0-dimensional. And the same sort of argument works for any hyperbolic group. You applying Bell-Dranishnikov, you get this. Okay. G is hyperbolic, yes. This is for hyperbolic, yeah. There are certainly groups with infinite asymptotic dimension. If they contain, for instance, the Thompson's group, if they contain z to the n for every n, z to the n has asymptotic dimension n, and the monotonicity holds. So it must be that Thompson's group has infinite asymptotic dimension. Now, one reason why you want finite asymptotic dimension is that this implies some conjectures in manifold theory. So the Novikov conjecture, this is the theorem of Guoliang Yu. So Guoliang Yu says that if G has a finite classifying space, finite BG, and asymptotic dimension of G is finite, then G satisfies the Novikov conjecture. So the Novikov conjecture is something about a manifold has these invariants called higher signature, and the Novikov conjecture predicts that if you have two manifolds that are homotopy equivalent, then they have the same higher signatures. So it's an important conjecture in manifold theory, and it depends on the group, on the fundamental group. But if the fundamental group satisfies this, then this is good. Okay. So that's about all I want to say about asymptotic dimension. And then I guess we only have like 9 minutes left. I won't say too much about mapping class groups, but I can at least get to maybe main theorems. And I guess if you want to see more details about what they'll say next, then you can come to my class next week. And I'll give you more details. All right, let's erase this. Okay, so mapping class groups are defined for surfaces. So if sigma is a surface like this, so there's some number of boundary components, and there's some number of handles, and then some number of punctures. So the mapping class group mod sigma. This is you take the orientation preserving homeomorphisms of sigma, which are identity on the boundary and also on the punctures. And you mod out by isotopy. Okay? And so for example, if I take the mapping class group of the disk with some number of punctures, say n punctures, then this is exactly the braid group on n strings. Okay. And the theorem that is joint work with Ken Bromberg and Koji Fujiwara. Well, there are really two parts. The first one is just that the asymptotic dimension of this group is finite. But moreover, you can embed it in a, it's quasi-asymmetric to some subset of a finite product of hyperbolic spaces. So mod sigma is quasi-asymmetric to some subset, say Z, inside a product y1 cross y2 yn, where each yi is hyperbolic. Okay, so mapping class groups are typically not hyperbolic, except when the surface is very small. Like for the torus, the mapping class group is SL2Z, and that's a hyperbolic group. But normally it's not hyperbolic because it contains this contains homeomorphisms that are supported on disjoint subsurfaces. So they'll commute, and they'll have a Z plus Z inside, and then there's no chance for hyperbolicity. But the next best thing is true. You can embed it in a quasi-asymmetric fashion into a finite product of hyperbolic spaces. Okay, so that's some kind of a statement about the large-scale geometry of the mapping class groups. Okay, so maybe in the last 5 minutes, I'll just give you some basic ideas of what goes in the proof. The large-scale geometry was developed by Mazur and Minsky, but in two very influential papers around 2000. So about some 15, 16 years ago. There's the Mazur-Minsky theory. Okay. So the basic object in the Mazur-Minsky theory is the curve complex of the surface. Okay, so there is a C of sigma. This is the curve complex. You can think of it as a graph, although it's really a complex. It has higher dimensional simplices. But what's important for us is just the one skeleton. So the vertices are isotopic classes of simple closed curves, and edges are disjointness. Okay, so for instance, if I have the surface here and I take this curve, call it A, and I take this curve and I call it B, and I take this curve and I call it C, then they define three vertices in this complex. A and B are connected by an edge, but C is not connected to either A or B because they intersect. Okay, now when the surface is small so that it doesn't admit disjoint curves, then you have to modify the definition, and I won't go into that. But the main theorem of the Mazur-Minsky, well, it's one of the main theorems, is that this complex is hyperbolic. Okay. Now so the mapping class group is going to act on the curve complex, but there will be lots of homeomorphisms that will not be really visible in the curve complex. If you have a subsurface and you have a homeomorphism of the subsurface, then any curve in the complement is going to be fixed. So a homeomorphism like that is going to have lots of fixed points in the curve complex. So you're not going to be able to understand the whole mapping class group just by looking at the curve complex. So the idea is to look at all curve complexes of all subsurfaces. Okay, so the idea is to look at curve complexes of subsurfaces. And there is a notion of subsurface projections that goes back to Mazur and Minsky that somehow relates the different curve complexes of different subsurfaces. And somehow what we do is we organize these. We take a collection of subsurfaces that pairwise intersect. You can have disjoint subsurfaces, obviously, But suppose you have a collection of subsurfaces that pairwise intersect. Then we organize those curve complexes of those subsurfaces into one of these spaces, yi. Because we can take the disjoint union and we connect them in some way, and we get a hyperbolic space in that way. And we break the collection of all subsurfaces into finitely many collections like that, so that within each collection you get this intersection property that any two intersect, and therefore can be organized into a space. So there are finitely many spaces like that we get. And this is all done in some equivariant way, so that the mapping class group is actually acting on this product by maybe permuting some of these y's. And then we use some more of the Minsky machinery, and we argue that this action, if you look at the orbit map of the action, then that's a quasi-asymmetric embedding. In other words, the orbit is this z. And it's quasi-asymmetric to the mapping class group, and it sits inside this product. And each of these y's has finite asymptotic dimension by the Bell-Dranishnikov theorem, because it's full of these curve complexes. And I should have mentioned that there's a theorem of Bell and Fujiwara that's important here, that the C has finite asymptotic dimension. So Bell Fujiwara showed that the asymptotic dimension of C is finite. And so if you put all that together, you get that all these y's have finite asymptotic dimension, and then by the product theorem, this whole thing has finite asymptotic dimension. The subset has finite asymptotic dimension, and then the mapping class group is quasi-asymmetric to it. In the meantime, since we finished this work, there was a paper by Betterstock, Hagen, and Sisto, where they improve. Our bound is somehow, from this proof, you get exponential bound. You get that the asymptotic dimension is bounded above by some exponential function of the complexity of the surface, but in terms of genus and boundary components and punctures. This other paper actually shows that the bound is quadratic. What we expect is that the bound should be linear, but we don't know how to prove that. Maybe I'll just finish by saying that my favorite thing to think about is to generalize this whole program to OutFN. OutFN is, I like to say it's an evil twin of mapping class groups. It's in many ways it's similar to mapping class groups, but it's more complicated. And at the moment we don't know how to generalize. There are various points in this proof that don't generalize to OutFN. But maybe next time something. We'll see. Okay, so thank you very much.